Okay, I know we've still got some audience members filing in, but we are at 10:30, so I do want to get started here. My name is Brendan Burrish. I'm a distinguished engineer. I've been at Cisco for 28 years and presenting at Cisco Live across the US, Europe, and Australia for the last decade. So today's session, Simple LeafSpine with a Touch of ToR, is going to be very focused on network designs for the modern data center. Now, we're at Thursday at Cisco Live, so I think everybody kind of knows the drill here. There's an app for WebEx that's got a Teams room. You're welcome to join. We will monitor these Teams room for questions through the 23rd. Slides should be available to you in the app as well. And in terms of questions for today's session, I will try to take them interactively and repeat them. We also will have a couple monitors that will run around with microphones. For lengthier questions, I guess all I would ask is we'll maybe take them at the conclusion of this session. So, in terms of what we're going to cover today, we'll quickly go through an introduction. There won't be much to that. Then we're going to go into kind of how DC network designs have evolved over the course of the last 10 to 15 years. Then we're going to get into the real meat of things. We'll talk about LeafSpine fat tree topologies. We're going to take a quick touch on some hardware considerations. Then we're going to pivot and move into VXLAN EVPN and how that applies and is very suitable for LeafSpine topologies. We'll talk about multi-fabric for a moment, and then I've got a couple migration examples that we'll step through, and then we'll draw to a close. So with that, let's start here in terms of introduction. And I think this is a very good illustration what we've kind of seen happen in the data center over the course of the last decade to decade and a half, where we had a lot of customers invest in traditional three-tier architecture. VPC was a very popular and very widely deployed technology, and we've now seen that start moving towards more of the routed fabric architectures. And VXLAN initially came to us as very crude kind of bridging and routing, and has now evolved to being a much more intelligent routing and segmentation-oriented technology that, again, is the prevailing technology we see deployed in the data center today. Now let's step back for a moment, and many of you may still be here because it's very proven and it's very widely deployed technology, but many of you may remember the FEX, a very widely and deployed and popular choice. This was a very common design we saw all over in terms of VPC to the northbound side. We had switches bundled together. We had port channels that moved to the southbound side, and then we had attached hosts beneath the FEXs. And one of the real appeals of this architecture was this notion of all of the management of the infrastructure was centralized to those VPC switches. And the FEXs were essentially slave-oriented devices to those switches. We had a lot of redundancy built in. We supported both dual attach and single attach hosts, and we were highly optimized around that architecture. You may remember then, soon after that, we had Fabric Path introduced, and some of you may have run Fabric Path, and this really brought us the first notion of LeafSpine, and we moved the transport between the aggregation and the leaf to Fabric Path. And Fabric Path, some of you may remember, was a Mac and Mac encapsulation. It was a layer 2 technology, and it actually, while it was popular in some areas, didn't gain as much standards traction as we had hoped. And then below the Fabric Path architecture, we still saw VPC as the prevailing technology for all of the host connectivity. Now, as we fast forward to about a decade ago and kind of where we are today, it's really moved to a VXLAN-oriented architecture where the fabric is IP, it's a layer 3 routed fabric. We still see VPC as the dominant technology to the southbound side. And we also see this notion of much more equal cost multipath focus in terms of full utilization of that cross-sectional bandwidth in the data center. Now, let's start talking about LeafSpine, and we're going to get into a variety of things as we move into this section of the presentation. We'll talk about topology. We're going to quickly talk about bandwidth and oversubscription and kind of how it is an important characteristic of the architecture. We'll talk a bit about hardware, and we're not going to really dwell on optics, but that is a consideration as you build out fat tree sorts of topologies. Now, as I said, many of you probably are either at one point had or still have that prevailing three-tier architecture we see on the left side, where you got VPC, you got a first hop routing protocol running HSRP or VRRP or something of that nature. And we see a lot of customers migrating or running both of these now, where we've introduced this CLOS fabric, a two-tier fabric where we got a leaf spine orientation to the fabric. Now, as you look at the CLOS fabric, we introduced some new vocabulary, as I said. Leaf and spine, it is in most cases a two-tier topology, and it is very commonly called fat tree. You hear it called folded CLOS. In a moment, we'll explain the three-stage kind of vocabulary here, and we actually have a five-stage variant of this as well. And in just a moment, I'll at least explain what we're talking about in terms of these stages. Now, in terms of three-stage, and as I said, it is a spines at the northbound side, leafs at the southbound side, and then all of your workloads attach to the leafs. Now, in terms of stages, we illustrate this by talking about an ingress stage, a middle stage, and an egress stage. And one of the nice things about fat tree topologies is all forwarding is completely symmetrical. We will either switch it at the local leaf, switch or route it rather, or if not, we will then move it to one of the spines and then one hop away, jump to another leaf. And this is where we get this notion of ingress, middle, and egress. The two-tier architecture, as I said, is an architecture where spines are going to be your kind of backbone class switch that are responsible for doing a lot of the heavy lifting and the IP forwarding. Leafs are where all of the devices that are going to attach to the fabric are going to get connected. And typically in today's day and age, we are seeing fabrics built at 40 and 100 and 400 gig on an increasing basis, meaning in the actual fabric itself. And host connectivity is typically 10 gig. We're seeing more adoption of 25 gig and even 50 gig now. Now, the other thing about fat tree or CLOS topology is it's a scale-out architecture. And what do we mean by that? It is extremely easy because of the way the fabric is aligned to actually grow the fabric. So we can add more bandwidth by simply increasing the number of spines. And because it's all layer 3 in the underlay, this is a non-disruptive exercise. If we want more access ports, or if we want more capacity at the leaf layer, we simply add more leaves. And the nice thing is, because every leaf connects to every spine connects to every leaf, but the leaves don't connect to leaves and spines don't connect to spines, we actually don't increase any of the notional oversubscription when we add more leaf capacity. The other thing that's very, very appealing about this technology is the resiliency aspects of it. And so because we use all of the forwarding or the available paths for forwarding, and we don't run spanning tree, it's an IP routed fabric, we have this very quick reconvergence. And should something go down, you kind of see it's just a simple math exercise. We lose one spine in a 4-spine topology, we've lost 25%. If we've gone wider than that to 8 spines, it's a 12.5% impact. You kind of see how the math is working here, but the architecture is intended and designed to be very, very capable of withstanding outages in all places in the network. And generally speaking, if we look at the leafs, the hosts are going to be dual attached. So again, we should be able to withstand virtually any leaf going down, or if you have to have structured software upgrades you're pushing into the fabric, it's very, very easy to manage and manipulate this particular technology. Now, the other thing everybody should know is the data center traffic patterns have been under a lot of duress and a lot of change over the last decade. There was a time that most of our traffic flowed north and south towards the internet. And with today's modern application orientation, the traffic flows are almost an 8-fold increase over that at an east-west level. So for every flow that goes north-south, we literally have 8x that is flowing east and west. And as a consequence, we see this architecture much more suitable to throughput and very, very high bandwidth implementations in the data center. And again, that's because of this cross-sectional bandwidth, this allocation and utilization of all paths in the network. Now, one of the other things that I think we've always been, or always attempted rather, to try to build networks around this idea of what is our oversubscription ratio. And in some of these technologies and the way some of the networks are tiered, that's not as easy as we would like it to be. In LeafSpine technologies or topologies, it is extremely easy to calculate oversubscription ratio. And you again see this is just a simple math problem. If I have 48 25 gig ports at the Leaf complex, that gives us 1.2 terabits. If I'm building my upstream fabric around 400 gig, you can very, very easily see it's a 3-to-1 subscription ratio. Adding spines doesn't change that, adding leafs doesn't change that. So we're in a very, very structured way. We've engineered the fabric so that we very well understand what those subscription ratios are and how we achieve improvements to those if we in fact want to do that. Now, one of the other things that we often get asked, and this is really the only part of the presentation I'm going to talk about hardware, is this question about, should I run a modular switch at the spine? Should I run a fixed switch? Should I run a fixed or a modular at the leaf? And if we think back to the conventional 3-tier architecture, particularly in larger networks, modular switches were very popular in the aggregation and the core because of some of the characteristics around high availability, dual soups, dual power supplies, and a very, very high concentration of ports. Because of the way that we're building LeafSpine networks today, we are seeing much more utilization of the fixed switch form factor, and that's because the spine layer has gotten very wide. We're not so much focused on 2 core switches that we try to feed everything into. Now, that shouldn't be taken to mean that we can't build around modular switches. We do have customers doing that. And it's important to recognize in our portfolio, we have switches in either variant, modular or fixed, that can take on the role of a leaf, a spine, a border leaf, a border spine, a border gateway, you name it. So what this comes down to in many cases is it's personal choice for you as a customer on what we're going to do in terms of hardware, right? As I said, we see more and more customers building around fixed form factor. Some of that's also because fixed form factor switches are easier to move around. They're easier to redeploy if you in fact are needing to do that, whereas something that's 10, 12, 14 RU gets to be very, very inert in the data center once it's installed. Now, at a hardware level, as I talked about, this will give you some idea what our portfolio looks like. So we've got 95 and 9800, there's a 94, and then that'll give you some indication of the fixed form factor switches that typically get deployed as spines. On the other hand, we have a similar kind of look and feel to the portfolio for leafs, in the sense that we've got a variety of these modular chassis, pretty much the same ones, and we've got slightly different SKUs that are going to be deployed at the leaf area in the network. Okay, let me pause and ask if there are any questions on kind of this initial setup, because now we're going to move into talking about VXLAN and how VXLAN is very much becoming the dominant transport that runs over this physical topology we just talked about. Go ahead, sir.
Take a hand.
Working now? Hello?
Yeah. Hi.
So in the situation where you're expanding your spine layer, that means that every one of the leaves has to have a connection to any expansion of spine layer. That means that at some point you're going to run out of your uplinks on the Leaf perspective. So would Super Spine on top of a spine would be a solution for that?
That's true. So the question was, at some point, depending on the kind of width or the port capacity at the leaf layer, we're going to run out of uplinks in terms of connecting to all spines. So at some point, if the spine widens to the point where I can't connect to all of them, typically what ends up happening is customers will move to multi-fabric architecture at that point. So they'll build another spine complex, start hanging leaves from them, and then we'll talk about how we run multi-site VXLAN architecture to glue those together.
Wonderful. Yeah.
Okay. Okay. All right, let's get into VXLAN here. And so one of the things that everybody's kind of got to get their head around here as we start talking about VXLAN is this notion of underlay overlay, right? And we have this vocabulary that talks about the underlay, which is effectively where I build all my physical connectivity. All of the folded cloth leaf spine topology we've been talking about is going to run in the underlay. And this is where we handle reachability for tunnel endpoints, okay? So this again is gonna typically be 10, 40, 100, even 400 gig in today's way of thinking. And then up on top of that, at a logical level, we are gonna run what's called an overlay control plane. And here is where the tunnels actually get built, and we have things like the virtual network and the virtual network identifier. Now, while this may seem new, we can actually think back to many technologies that have been geared at overlays. We've had a tremendous number of them. You can go all the way back to GRE being probably one of the first ones you may or may not have utilized. MPLS is an overlay. Fabric Path was an overlay. IPsec is an overlay. The thing we like so much about VXLAN is, you see here we have two types of overlays. We have an L2 overlay and we have an L3 overlay. VXLAN happens to be one of the only transports that affords us this hybrid notion, where we can run layer 2 and layer 3 services using a single protocol. So it gives us a lot more efficiency in the data center in a lot of cases. So think back to 3-tier architecture, and we're managing things like spanning tree in the L2 complex. We're managing routing protocols and first hop gateway protocols in the routing complex, right? So that it's not consistent. We've grown accustomed to how to deal with that, but you could make a case that this makes life easier as we move to kind of this single protocol orientation, this overlay. Now, VXLAN is a standard, as is its corresponding control plane. So as you kind of look through this, VXLAN is the data plane encapsulation. Okay, it is UDP based. You see the RFC that we follow here. It is transport independent. Okay, as I talked about, we typically see a layer 3 IP routed transport at the underlay level. Now, the other thing VXLAN gives us is this highly flexible namespace. Some of you may know that the VLAN namespace is an 8-bit part of the header that gives us 4,000 VLANs for which we can use, 4096 specifically. The VXLAN architecture gives us 3-fold larger address space at 24 bits and gives us 16 million segments. So much more flexible, much more oriented at segmentation types of deployments. Now, EVPN runs on top of that. Again, a standards-based control plane. You see the RFC we're following here. Good news is, if you've run BGP and you've used BGP, you actually know more about EVPN than you think, because we're using BGP and the extended address family in the EVPN control path to actually build all of the connectivity. And this can run over a variety of underlays that we talked about here. And there's many use cases. We're going to go into a variety of those as we kind of dig through the presentation. Now, why would we run VXLAN versus kind of traditional technology? And what we're seeing is more and more customers are telling us things like, well, listen, my VLANs are really restricting my ability to build in the data center the way I want to. Or I have a server team that's telling me I have to have layer 2 reachability across all parts of the data center. Or maybe I've run into the 4K limitation around VLANs. Or maybe I've built a network that spanning tree doesn't allow me to fully utilize all the deployed paths. And by using an IP-based underlay, we now have ECMP and we have larger cross-sectional bandwidth. And as you might imagine, we also have a lot of customers telling us they want more and more multi-tenancy oriented connectivity in the data center. VXLAN generally will address all of these asks at a customer level. Now, as I said, at a topology level, while we don't have to run it over LeafSpine, that is the prevailing technology that we see in terms of how we are structuring the underlay. And as I said, we typically then also see it being a layer 3 IP routed underlay running something like OSPF, ISIS, BGP. We'll talk about that in a moment. And the other thing to understand about VXLAN is we use a unicast VXLAN tunnel to carry all the unicast traffic. And then there's also something known as the multi-destination service, or what we call the BUM service. Multicast, unknown unicast, and broadcast are either carried by multicast or they are carried by something known as ingress replication. And that's how the protocol actually carries the varying types of frames that we need to carry through the network. Now, at a vocabulary level, some things that you need to understand around VXLAN would include the basics here. So a VXLAN segment, you can really analogize to an L2 broadcast domain. Think of it as a VLAN. At a corresponding level, we have something known as the VXLAN network identifier, and we have to map that to its counterpart on the Ethernet side. So we have VLAN X equates to VNID Y. And then the most important part of this is this notion of the VTEP, the virtual tunnel endpoint that gets dynamically built between leaves and allows us to structure this in a way such that all of the traffic can be carried at L2 and L3. We carry host routes, and we will carry all the prefix routing as part of this. Now, let's go back to some kind of roles and responsibilities in the network. And we talked about this a bit, but it's worth reiterating that at the leaf level, we typically are seeing all of our host connectivity handled here. Servers, bare metal, VM, container, you name it, firewall, application delivery controller, things of that nature are typically always going to connect at the leaf layer. We also, this is where we perform all the encapsulation and de-encapsulation for VXLAN purposes, and I'm going to explain that in a little more detail in a moment. The other thing that's so appealing about VXLAN is we move away from the idea of having to run a first hop routing protocol, HSRP, VRRP, GLBP, and we introduce something called the Anycast gateway. Meaning all switches at the leaf layer, if they have a VLAN configured across them, are capable of acting as the default gateway. And the device that is looking for default gateway will reach out to the closest device in the network, and that will act as default gateway. So I've now horizontally scaled my default gateway in a much more scalable manner. Okay. The other thing that the leaf layer does is typically provides this connectivity to the rest of the network. Because we think about the fabric and all the attached devices in the fabric, and then we think about how do we get to the rest of the network? How do we reach the campus? How do we reach the WAN? How do we reach the internet? And that's all through something known as a border leaf, a slightly modified variant of the leaf role. And that's the ingress and egress point into the fabric. Now the spines, as I said, are different. The interesting thing about the spines is unless they are a border device, they do not run VTEPs. They are IP forwarders, and I'll explain that in a moment here. But it's important to recognize that the spines run one of these underlay routing protocols. They establish relationships with all the switches for the purpose of exchanging routes, and they do that because they act as a route reflector. We talked about the fact that EVPN is very, very much based on BGP, and route reflectors, as we know in BGP, are responsible for learning and distributing routing information. So as we learn host routes to leaf level, we will announce them to the spine, and the spine will radiate them out to the rest of the leafs. And that's how we announce and advertise all of the host reachability in the fabric. In many cases, the spines are also going to be my rendezvous points for that multicast, broadcast unknown multicast service. Or if you're running multicast in the fabric, the spines are typically doing that or performing that role. Now, let's look at a structured topology that typically is what we're going to see customers build, where we've got 4 spines across the top. We've got a variety of leaves here that are illustrated across the bottom. As I talked about, everything is fully meshed. Leaves don't connect to leaves, spines don't connect to spines, but all leaves connect to all spines. And this is typically always the best practices that we recommend how you go about building these types of networks. The fabric, the underlay, as we talked about, will be an IP routed fabric that supports ECMP. And you have the elective option to run either an IGP, those would be OSPF or ISIS, or you may run BGP in the underlay. We're not going to get into a lot of details on what those how you go about making those choices. Typically, it's slightly easier to run an interior gateway protocol in the underlay. However, if you like BGP, you absolutely can do it, and we absolutely support it. As I talked about, the links are layer 3 point-to-point links. Again, we're looking to simplify things. We don't want SVIs in this part of the network. We generally want point-to-point links. And then we don't have to do things like designated router, backup designated router if you're running OSPF. So we're really trying to simplify and make this a very lean part of the architecture. Now, as I said, at the leaf level, this is where we're going to introduce the LAN segments and where you're going to see all the peripherals attached to the network, the workloads. You'll notice we're also illustrating some of those are dual attached, some are single attached. Wherever possible, we recommend dual attaching everything if you can. If you do not, we have capabilities to certainly optimize forwarding for those devices. Now, we talked about the fact that VPC is still the prevailing technology that runs to the south of the leaf. Okay, so we're going to run port channels. We're going to tie the 2 switches together as one virtual kind of identified switch. And then to the north of the leaf, we run VXLAN. And those are tightly coupled together in terms of technologies and protocols, how they interact with one another to create this folded cloth overlay-based topology. The other thing we talk about here, of course, is the overlay. Okay, and the overlay, as I said, is responsible, and let's go to the next slide, right? So the overlay introduces this notion of the VTEPs. The VTEPs are going to be dynamically established leaf to leaf, and as a consequence, the namespace is only known to the leafs. So we talked about the fact that the spines don't have any VTEPs. They don't need to understand that. The spines are just next hop IP forwarders. So again, lightweight, very lean, and it's very intentionally designed this way. And so those leafs are going to dynamically connect to one another, and they will then also have the responsibility of taking all of these individual 32-bit or /32 host routes and announcing them to the network. And they do that, if you go back 2 slides here, by way of the route reflector we talked about, where we're going to announce those into the spine, and then the route reflectors will radiate those out to the rest of the leafs. Okay, so all lookups in this case are known to all leafs in terms of /32 host-based routes. Any questions at this point about what we've gone through here? Okay, let's talk a little bit about what is Ethernet VPN, or what we shorten to EVPN. We talked about the fact that VXLAN is the data encapsulation. We talked about some of the standardization of it. In the early times of VXLAN, we had no control plane, and we used a very crude way of forwarding called flood and learn. And by its very definition, we know that this is not appealing because we flood and we learn in a very inefficient manner. Think spanning tree, think other sorts of technologies that have typically not been that well liked. So all of the learning is done by observing packets in the network. So in the absence of a control plane in the early days, we were very much of the opinion that VXLAN was not suitable for large-scale deployments. Didn't really have good multipath support, it had a huge address space, and it came with a lot of risk. The whole notion of adding EVPN as a control path element on top of VXLAN was so that we can bring greater levels of stability into the network. Okay, and now learning is done through EVPN, and all the announcements are handled through EVPN. So we talked about the fact that as a device attaches to the network and announces itself, it's going to then be carried in through EVPN up to the spines, route reflected out to the remainder of the leafs. So everybody knows how to reach everyone else in the fabric. And so as you might imagine, what EVPN brought us was optimization of broadcast unknown unicast and multicast traffic. Layer 3 became optimized. We're now capable of multi-homing, and we have things like peer auto discovery, peer authentication, host mobility. So a lot of good things came about as a result of introducing that structured control plane on top of VXLAN. Questions about this? Okay. Now, as we look at EVPN, it's important to recognize that EVPN is the technology that we use to, again, announce routes throughout the network. And there are three ways, there's actually more than that, there's really three ways that you need to be thinking about how routes get announced inside of EVPN. We have MAC-based routes, we have MAC and IP-based routes, and we have prefix routes. And we're going to go through what each one of those is in a moment, okay? Because of the EVPN structured control plane, we don't do any flooding in the fabric. So again, that's a good thing. And where we need to flood, we're using that very structured broadcast, unknown unicast, and multicast service to do it. The tunnel encapsulation protocol, right, uses multi-protocol BGP EVPN as the control plane. And as I said, it introduces this notion of an extended address family as part of BGP. Now, we talked about the fact that you really need to concentrate and understand that there are three primary types of routes that we need to know inside of EVPN. The type 2 routes, and there are two variants. There's an A and a B substrate to the type 2 routes. There's a MAC only. Think of a host not running an IP stack, and we still have some of those where they're going to announce only a MAC address and MAC information. Typically, that's going to be bridging information, and so it's going to use something known as a layer 2 VNI, virtual network identifier, and that's the Ethernet service identifier we use. For the vast majority of hosts in kind of the modern data center architecture, they're going to run an IP stack, of course, and so they're going to run the B variant of the type 2 route. It'll be a MAC and IP announcement, so we're going to have both L2 bridging and L3 routing information. We talked about the fact one of the reasons we like VXLAN so well is because it supports bridging and routing concurrently, integrated routing and bridging. The other really important one is these type 5s, right? Because we've talked a lot about the fact that the type 2s are how we announce all of the hosts, /32s, but prefix routes, things that routers would announce to us about other networks and things of that nature, are going to be carried as type 5 routes. Okay, so anytime you're looking through a routing table, really the ones you're going to be paying closest attention to are going to be the type 2s and the type 5s. And again, there is what we just talked about here, right? So you have the A and B variant of the type 2s. All of the host routing that's how we carry that. And then we have the prefix route. So it's going to be IP only because routers and other devices that are carrying prefix information are going to be responsible for announcing that. Any questions about this or anything we've covered so far? Okay. We talked about the fact that BGP and EVPN are very, very close cousins of one another. And so a lot of what we use inside of VXLAN, or EVPN more specifically, is going to be well-known and well-understood concepts. I think everybody knows and understands what a VRF is. And a VRF is the way that we carry routing information inside of VXLAN. You know, you have all the hosts, and we have attaching hosts, and then as part of the service that they inherit, as part of the tenant, they get a VRF associated with the VNI that they're a member of. We also use the route distinguisher concept. Some of you may know this very well from things like MPLS. It's an 8-bit identifier that tells us who's who in the zoo in the terms of who has announced that 32-bit route. That's via the route distinguisher, and you may know that as a VPN IP prefix if you're an MPLS literate individual. The route target is used for devices to understand what they will import and export in terms of learning routing information. So we don't want to inefficiently announce routes to everyone if they don't need to know that. And so the way we distribute routing information as part of the VRF is via the route target. So the route distinguisher will identify who is announcing it, and the target will tell the egress device what to bring in terms of learning. And then, as I said, we've got the VPN address family, which is an extended address family as part of BGP. Okay. Now, let's look at a tenant. We talked about the fact that VXLAN is very multi-tenant oriented. And typically inside of a tenant, you're going to have a variety of VLANs. In this case, we're describing A, B, and out to N. And each of those, as I said earlier, is going to have a VNI, a virtual network identifier associated with it. And that virtual network identifier is going to have a corresponding VLAN that it is mapped to. VNI A matches or maps to VLAN A, right? And this is how we translate between the Ethernet namespace and the VXLAN EVPN namespace. And then as part of that tenant, there will be an SVI, and as you might imagine, this is where the VRF or the layer 3 routing service runs. So inside of a tenant, this is a structured view of kind of the piece parts that represent that tenant. This also explains to you, right, traffic within one layer 2 VNI is bridged. That makes sense, right? It's going to be all layer 2, so we will bridge that traffic. Traffic between L2 VNIs is routed. Now, one thing we cover in the tutorial that I don't have a slide on here, that I at least want to call out here is, some of you may remember from Ethernet, and it's been around since the beginning, is that a router does not change the MAC address, but it changes the next hop, right? So routers introduce something known as the router MAC. They will ARP for their partner, and they will use router MACs to talk to one another. They will preserve the attached device's source MAC address. Right? Everybody knows this. The reason I raise this is VXLAN does the exact same thing. So when I hit that edge router via a device, source MAC's going to come in, router is going to change to his MAC, and inside the frames, you will see something called the router MAC. The only difference is the next hop, instead of an IP address, is going to be what? A VTEP, right? It's going to be another leaf somewhere else, because we ARP for that other router to figure out who that is. And that's how we handle all of the packet forwarding inside of VXLAN. So it's the same as Ethernet. That's the good news. So if you know and understand Ethernet, again, you know and understand VXLAN more than you may or may not think. So let's talk a little bit about how VXLAN networks scale. So I think we had a question earlier here about when I exhaust spine capacity, okay? Or when I run out of uplinks and I naturally have to introduce a second fabric, right? And there are a variety of reasons why a second fabric may get introduced. It may be because of this, where we've just outgrown the physical capacity of the switches that are in place. It may be because we want to reduce our fault domain and build another fabric such that if there's an event somewhere, A doesn't ripple to B, B doesn't ripple to A, and things of that nature. Or you might be a customer that's larger and have multiple data centers, in which case you would naturally be building a fabric in each of the data centers. Now, as you can kind of see from the illustration here, we are depicting a VXLAN fabric in both networks. And you see the LeafSpine topology, the fat tree orientation to it. It looks the same as what we've been talking about for the last 40 to 45 minutes. And so the gold line is illustrating how we do forwarding inside of that single fabric. We would switch locally if devices are attached here. Everything else will go up through the spine and will be VTEP to VTEP communication. Same thing in fabric B. Now, the reason we describe this is because we see some customers, when they introduce the superspine layer, and let's talk about the superspine for a moment. So the superspine is obviously the way that we start to physically glue these networks together. Now, for simplification of illustration, we draw it in a way that would imply that you have a lot of fiber, because a lot of fiber would be required to hook it up like you see illustrated here. You certainly have that elective to hook it up this way, or alternately, if you have an IP service sitting connecting these two fabrics together, we can connect to that router or routers. It doesn't have to be full mesh, and we can use something called a route server to then distribute that information to the rest of the spines. So it either can be meshed, i.e. I have fiber, or we can use that layer 3 service to connect things. Now, the point I want to make here is, in many cases when two fabrics are built, I do have needs to support this red traffic pattern. I have a device in data center A that needs to talk to a device in data center B. What we don't want is to build a stretched overlay. Because what I've done here is defeated the purpose of why I built this in the physical way that I did in the first place. I just bolted the data centers together logically by creating that extended, stretched overlay, okay? So we want to be able to support the ability to carry traffic this way, but we don't want to do it by creating this end-to-end overlay. So what we've done, or what we've introduced, is something known as multi-site VXLAN, okay? And multi-site VXLAN, of course, preserves the notion that I have needs for local connectivity, the kind of gold or yellow colored line here, but then I'm going to introduce a net new multi-site overlay. So now reachability is still preserved, right? I can still get from Leaf 1, Fabric 1 to Leaf N and Fabric 2, but I have a dedicated multi-site overlay. Think of this as OTV, VPLS, MPLS, something like that. Just happens to be running VXLAN in this case. The nice thing here is we decapsulate and terminate everything, and then we build net new VTEPs as a dedicated multi-site overlay. So all of your reachability is preserved in terms of how I communicate across the fabrics, but I now have not glued the data centers together. So I literally have multiple logical data centers. Now, how we do this is by introducing this notion of something called the border gateways. We talked about the fact early on that we need to identify what devices' role in the VXLAN network is. They're a leaf, they're a spine, they're a border leaf, they're a border spine. Okay, border gateway becomes a very, very key component of the VXLAN architecture. And what we introduce here, which shouldn't really surprise anybody, is this notion of a multi-site VIP. Okay? And how this works is anything known in the local overlay in Site 1 will be handled at a forwarding level inside of Site 1, leaf to leaf through the spines. Anything I don't know, think of it as a default route concept, I will send it to the border leaf. And the border leaf will have an established relationship with his constituent border leafs. It'll basically say, if you don't know, go to 10.2.2.222, because he knows. We will decapsulate at the spine. We will re-encapsulate or establish a net new encapsulation. And this is where we introduce this idea that the spines or the border gateways are now building VTEPs. Remember, we talked about VTEPs are only done at the leaf. Spines are not VTEP aware. They're IP forwarders. In this case, because I'm now building an overlay, a dedicated multi-site overlay, the spines or the border gateways in this case are going to be now VTEP forwarders. Any questions about this? Figured we might have one here. Go ahead. Can you stretch an IP address or run it in both sites? Is that what you're asking, a subnet? You can. So the question was, can I have the same subnet in two places? You absolutely can do that. And as I said, the border gateways will basically know the local /32 host routes. Anything not known, they're going to have an entry in the routing table that says, go over to 10.1.1.111. And then he'll know, right? So you can absolutely stretch a VNI across the fabric. We even support translation if you have duplicates. We support something called downstream VNI. You can go look it up. I don't have slides on it today, but we can do the equivalent of natting if you need to do that. But we absolutely can stretch the VLANs, and because we re-encapsulate at the multi-site overlay, none of this is flooded, all right? And even ARP and other things like that are re-originated inside of the multi-site overlay. So an ARP doesn't ripple. We will create a net new frame, carry it across the multi-site overlay, decapsulate it, and then drop it off. That answer your question? Okay. Other questions? Let's go here.
This also all works with IPv6?
Does it work with IPv6? Yes. So we support IPv6 in the underlay. So you absolutely can run a v6 network as the underlying transport in the underlay if you wish. Yes.
What if you do have 3 sites?
What if you have 3 sites? Good question. So our multi-site technology allows termination of up to 12 sites in a single structured multi-site design. One caveat there is we do have some customers that if they only have 2 sites will back-to-back the border gateways to try to preserve fiber and do some things like that. In a base 2 situation, you can do back-to-back. The minute you have 3, we don't allow that to be meshed. You got to go to a super spine or that IP disintermediating layer and use a route server. But we support up to 12 sites today in a multi-site architecture. Yes.
I'm sorry, you have used border gateways interchangeably with spines. So do you not need spine and border gateway?
Good question. So the question he asked was, does the border gateway run on the spine or can it be dedicated? And we support both. So if you want to essentially create a sandwich out of a single switch and have the spine function run to the south and the border gateway to the north, you can do that. For more scalable environments, typically customers would then attach a dedicated border gateway or border gateways. So we do it, we support it either way. Okay.
Just a quick question. You're explaining, you just told us that there is a 12 sites in the situation that you can expand or you can stretch to. And I would imagine that when a packet arrives to the border gateway, then they have to be replicated so the BOM traffic will have to be replicated through the sites. So what kind of replication? Can we use multicast replication on top of that as well?
Very good question. So we talked about, the question was, how do we do broadcast, unknown unicast, and multicast handling in the overlay? Okay, so we talked about the fact that in each individual fabric, here, you get the option to either run multicast or head-end ingress replication to carry that multi-destination traffic. In the multi-site overlay, we default this to run ingress replication. And today, we don't support multicast. That has been asked and we have evaluated that. Part of the reason we chose ingress replication is if you're running a public transport network to buckle these together, we see carriers in some cases that won't carry multicast traffic. So we defaulted to run unicast, figuring that that would cover a wider spectrum of use cases. You can still run multicast or head-end replication in either fabric, and you can mix and match. It's just in the multi-site overlay, ingress replication only. Okay.
Is it a tunnel under tunnel?
One more time.
Is it a tunnel under tunnel, like VXLAN tunnel terminating at the overlay one, and one more overlay?
Yes. So we decapsulate. If we don't know it locally, we're going to decapsulate, and the spine's going to have another, or the border gateway rather, is going to build a VTEP to its adjacent border gateway partner. Okay?
Thank you.
All right. So, again, the whole notion here is if you're going to go to the trouble of building out multiple fabrics, you have multiple data centers, we really want to preserve all of the benefits of that isolation that you've created. And this is why the multi-site architecture has been introduced. Okay. Now, the last thing I want to do, and here we always have to make some choices, but I want to go through a couple migration examples. And they're primarily focused on, if you have classic architecture, how would you introduce VXLAN and how would you migrate? Okay, in this case, we've chosen to illustrate FEX, but it's equally applicable to fabric path if you have that. But as you might imagine, the most common way we see this done is to introduce a side-by-side in a net new fabric and run them in parallel. Now, the first thing that has to happen here, if you're going to do that, is I have to provide L2 connectivity between the fabrics. And I have to do that because the next thing I have to start doing is migrating endpoints. And I got to have an L2 transit path for these to be able to communicate with one another during the migration. Now, after that, we also then have to decide when the default gateway is going to move. Because default gateway can only be in one place. We know that, right? It's probably running HSRP or something like that here, and it's running Anycast over here. So inevitably, there will be some period of time where some set of hosts will be penalized, right? Either the host in the old network will have to go get default gateway in the new network, or vice versa. So you have to kind of be thoughtful in terms of when you're going to migrate the default gateway, right? When you're going to move it to the VXLAN side, and then, as you might imagine, the punchline here is we decommission the old fabric. Now, let's go through some examples about how we actually systematically step through a couple of these migrations. And in this case, we're going to first illustrate it where I've constrained racks. Right? This is a slightly tougher migration scenario, right? And again, as I talked about, we're illustrating a pre-existing 3-tier architecture based on FEX. So the first thing we're going to do here is, and again, we say rack space constraints, but we're taking the liberty of saying we have a little bit of rack space. So I first introduce spines and leafs in one of the racks. Just 2 in each case, and that's how I get my structured cloth fabric in place. The next thing I have to do is add a pair of borders. Border leafs, border spines, we can orient how we want, and then I'm going to connect them, okay? You may also be running a controller, NDFC, something like that, if you're not actually using, fingers to configure everything. So if you're in fact running an NDFC controller, this would be the point in time we'd introduce that as well. Now, the next thing that's going to happen, as you might imagine, is these pre-existing end-of-row switches are now going to get attached to the leafs, okay, in that rack, and provide L2 and L3 services. Remember, we talked about the fact we have to provide connectivity, and we have to provide a stub to get in and out of the default gateway. Then I'm going to disconnect those end-of-row switches from the aggregation, right? So in the past, we had them dual attached here. I'm going to disconnect those. And then, as you might imagine, I'm going to decommission them. And then the last thing that's going to happen here is you'll notice that we kind of very carefully flipped one of those FEXs into a leaf switch. We now attach the server. We would do this one leg at a time. Hopefully everything is dual attached, so this is non-disruptive. And then we would complete that exercise where everything moves to dual leaf in all of the racks. And then we would decommission the remaining equipment. So at that point, through a series of steps, this is in theory a non-disruptive migration, or it can be if it would be carefully planned. Now, it's a little easier exercise if I have more available rack space, but we do step through this example. Again, pre-existing FEX classic architecture with aggregation switches, FEXs, and then servers sitting in the rack complexes. First thing I'm going to do, same thing I did in the last case, but because I have more freedom, I'm going to build the spines and I'm going to get the leafs positioned in all the racks. If you remember in the constrained case, I had the spines and the leafs in the left side rack, and it wasn't until the very last step I moved leafs to displace FEXs. I have a little more freedom here. As you again might imagine, we will introduce the border gateways and connect them to the core and also attach them to the spines. And if you're running a controller, here's where we would introduce that. Like we did in the last case, I'm going to attach the end of row devices, right? I'm going to start swapping servers, and eventually I'm going to step it through such that and I don't see, I guess we didn't illustrate this, but the last step, of course, would be we would decommission that top rail of stuff. I must have missed a click in the animation here. So I don't see that happen, all right? So we've got a couple minutes left. What I want to conclude with here is the following, right? So what you hopefully took from today is, we're in the midst of some changes going on in the data center. We went through prevailing three-tier architectures, very popularized around FEX and fabric path to some degree, but the vast majority of the technology in the data center is either moving to just a raw IP transport of some sort, or in more cases, what we talked about today, VXLAN. There's also always inevitably this question about the cost of FEXs, because one of the things that was very appealing about FEXs is they were inexpensive. They were very economical. Most of our FEXs have been retired. We don't sell them anymore, but if you look carefully, most of our leaf switches are fairly close in terms of cost to FEX. And obviously the benefits are we get a full-blown switching complex versus something that would be more akin to a hub, if you will, because it slaves off of the centralized switches. And then the last thing we talked about was, if you're going to move to VXLAN or introduce it, how do we gracefully migrate? Because there's nothing worse than bringing net new technology into the data center and then not having an understanding of how either to coexist or how to migrate without having outages occur, okay? So, as I think we have asked all week, please fill out your surveys. I'm a session group manager in Europe and the US, so I do all the curriculum planning. The reason I tell you this is we want to know the sessions that are good, we want to know the sessions that are bad, or that need to be improved, rather, so we know what to bring back, all right? So we value your feedback. If we did well today, tell us. If we need to improve today, tell us. Okay, so, and I think there is a place where you can go get this t-shirt. I don't claim to know where that is. It's Thursday, so it's very likely we're sold out of t-shirts. I don't know. And then continuing education, of course. There's a variety of places for you to continue to learn as the week wears on. We are nearing the end, of course, here because it's Thursday, but we still got today and I think bits of tomorrow. And with that, we have a grand total of 1 minute left, so we are going to finish on time. That's always a good thing. I'm happy to take more questions if we have them. Otherwise, I will stay as long as I'm able before we start the next session and take questions individually if you wish. So I appreciate everybody coming. I know it's been a long week. Hopefully the session met your objectives and we went through some things that will help you kind of learn where we think we are in the evolution of the data center. And so with that, I'm done.